Good morning. Welcome to Transfer Phenomena Bioprocessing Week 2. So, today we will discuss about the rheology in bioprocess engineering. So, what do you mean rheology? The rheology is the flow of study. The rheo is the flow, then the logy is study. So, the rheology mainly discuss about the flow and then deformation of material like both solids and liquids. So, then we have to understand about the flow and the deformation behavior in biological fluids. Especially the biological fluids can be a fermentation in broth, blood, plasma, then protein, then polysaccharide solutions. So, some of the key rheological properties are viscosity, shear stress, then shear strain. So, what is the importance of transfer phenomena here? So, it governs mainly the movement and transfers. Already I discussed the movement and transfer is a function of velocity gradient, then the mixing efficiency, then the mass transfer is a function of concentration, and then bioreactor dynamics. These are the importance of transfer phenomena here. Then when you want to scale up the bioprocess system, sometime Newtonian to non-Newtonian, so that we have to account here how to scale up the process. So, these are the very importance for the transfer phenomena. So, then what is the role in the transfer phenomena, then importance here? So, mainly the process optimization is very important here, because when you want to make it to lab scale to pilot scale or bioreactor the large scale level, this one. So, the process optimization is very important. There is a lot of variables are here. It starts with pH and different type of variables are there, but that how you have to optimize, because we have so many variables, but that you have to optimize, then you have to get the correct efficiency of the product. So, that is the reason the process optimization is one of the very important here. Then the product quality, of course, when you do the bioreactor process or any type of reactor process, the product quality is important, especially here the pharmaceutical product, that the stability you have to see whether it's properly this one, that's a product quality is one of the main another role of the transfer from bioprocess. Then scalability, that already I discussed how from lab to industrial scale, then how to scale up that one, that definitely we need the rheology studies. Without rheology knowledge, we cannot do scale up the process. So, what are the role of in the transfer phenomena and importance for these transfers? So, movement and transfers, already the movement and transfer is the function of velocity or velocity gradient or velocity driving force. These are all the movement and transfers. So, definitely it predicts how the fluid will move through pipe and the reactor and other equipments, because normally the fluids move on to other one. So, definitely we have to use all the pipe and reactor or here. Then definitely what type of the pump selection we have to do here and how much energy requirement for mixing, but all together we need definitely thorough knowledge about the movement and transfer. Then the mass transfers, the main rheological properties, particularly viscosity, many other parameters are there. So, how the viscosity influence the diffusion and convection, that also we will discuss here. Then other one is for how the affects the transport of nutrients and the removal of waste products. The heat transfer, the viscosity is the mainly how the affecting the heat transfer from especially the fermenters, then the heat exchangers. These all type of process, how the heat transfer taking place to one place to other one. Say example, you want to hot fluid to cold fluid. So, especially we will use for the heat exchanger, double pipe heat exchanger, then shell and tube heat exchanger, all type of exchanger will use. There is the use of that one, how the heat transfer from one to other liquids, like hot to cold for that purpose. So, now what is the fluid here? The fluid is continuously the deformation subject to whenever if you apply some shear stress. If stress is there, the fluid is not constant. Unlike the solid is always, it's like we can take a rest, but if or other any type of flow, gas or liquid, definitely the flow always will be there. So, the natural this one you have to apply for tangential stress. Normally the both liquid and gases always we called as the fluids. So, the shear force is very important here. You just see here the stack of thin parallel plates are there. You just apply for tangential force, how the plates slides each other over each other. So, this I am just showing here the both this one. So, another the example here, this is a stirred tank bioreactor, how this is working here, how this the fluid properties are important for here. So, example again the shear stress is the main factor of the fluid motion here. Without shear definitely it should be like static and there is no movements. So, definitely somewhere the shear stress should be there. The stirred bioreactor, just see here the medium and we added acid base. Here you can see this one medium, then acid base, then next is the bottled zinc gas always there. So, the outside CST as a continuous stirred tank reactor is we can use in a chemical purpose or in biological purpose or whatever this one. But here these are the one, then the output here the gas sampling, you can see gas sampling and exhaust the point here, same way for liquid sampling also. So, this is just an example of how the CSTR works. Anyway, we will discuss more on the MATLAB programming, how this bioreactor works, we will discuss in the forthcoming classes here. So, mainly the process industries, these are the very important for fluids, especially the raw material then finished products. The both are the in terms of fluids, but how to handle the fluids, because when you take even raw material and again the product, both are the fluids and how to transfer, how to handle, how to store and how to pump the liquids, many things are here. And this space especially this example of the food industry. So, what are the different type of this one, that like thin liquid is there, then thick liquid is there, gases. Thin liquid you can take milk, then water, then fruit juice, all the thin liquids. Thick liquid if you take, definitely this like honey, oil, jam, whatever, all the thick liquid, the more viscous, we can say more viscous liquids that one. Of course, the gas always will use the bioreactor like air, nitrogen, carbon dioxide, all this one. So, definitely we need thorough knowledge, we need about the governing of the flow of fluids with the machinery equipment, then only we can use these instruments. Then another reason, the nature of flow pipes and the reactors mainly depend on the power input of the, how much power input of system and the physical characteristics of fluids. So, they both are very important. Say example, take a fermenter, the fermenter is here, the fluid properties mainly affect the process, how much energy requirement and how much effectiveness mixing can be done here, then only we can get a good product and the success of equipment and scale up also. The fluid bioprocess mainly contain lot of suspended solids, it contain more than one phase, sometimes gas phase, liquid phase, sometimes solid phase also, but that is normally not happen that one. But all phases are there, then how it behave as a sometimes in Newtonian fluids to non-Newtonian properties, but how these affection here, this one. So, you have to discuss all about how the flow behavior and the complicated analysis, the bioprocess design. So, before starts this one, just a simple the fluid mechanics, I want to discuss about how the fluid mechanics movement and transfer, we can classify two branches here. So, one is the fluid statics, then another one is the fluid dynamic. The static is when fluids are at rest, the dynamic is when the fluid is in motion. So, here you just see the fluids in motion here when it is a dynamics. So, we can say this way also, the dynamic we can always call unsteady state, but here the fluid statics, the steady state. So, what is steady state here is like time, here time no need, because time no, but when you use the dynamics you have to account the time, because whenever you use the fluid dynamics, of course, this the name itself dynamics, so you have to account the time is the factor of here. So, we will discuss the fluid statics and fluid dynamics, the basic things here. Before that, the fluid statics, the simple example here. So, you assume like we have the pressure static fluid, it starts with the A naught is the A naught area of the one first one, the A1, we have assumed the surface here A naught A1, then A2, and wherever the pressure act in the A naught, that is called as the P naught, then the A1 point we call as a P1, then the A2 is the P2. So, the height of this one, the A2 to A1 we called as the H3, the height of that one. The same way for A1 to A naught we call as the H1 height of that one, but the overall height we are called as a H2. Okay. But here the pressure in the surface always throughout the same point always same, that is the basic concept here, but pressure varies with respect to elevation. Okay, but pressure is constant the same wherever the same point. Say example, you want to measure this point, everywhere the pressure is same. That's only they mentioned here, but here the another assumption here, the A0, A1, A2 all are same, and the pressure of the fluid here above the P0 we called as a P0. Of course, the pressure is the force per unit area. So, when you want to calculate, it's very simple, it's not very, but when you use for MATLAB, maybe we do more modeling at some point of that one, but it's the basic things here. So, when you normally this is called the force equal to F equal to mg. So, that's only here mg, and then pressure we always call it P equal to F by A, pressure equal to force per unit area. The total mass of fluid m, we can call m equal to H2A rho. So, here the H2 is meter, H2 is the meter, then area is the meter square, then the density is the kg per meter cube. So, finally, we get in terms of mass of fluid here. Again you substitute this all, okay, F equal to P into A force, F equal to H2 into A rho g. So, then we can write P equal to H2 rho g. We will always use this one is the pressure for here, the P equal to F by A, or we can use H2 rho g. So, I want to measure now P2, the P2 pressure, so you have to add here, I will go back. So, the P2 I want to measure P2, then P0 plus this one you have to add, okay, the P0 plus this one you have to add, that is only here the P2 equal to H2 rho g plus P0. Same way for pressure 1, P1, go back P1, the P1 here, then H1 this one plus P0, this point you want to measure. So, the P1 equal to then P0 plus H1 rho g. This is for just basic here. So, when you want to measure the pressure difference, the P2 minus P1, the definitely difference between H2 minus H1 of into rho g. I will go back, the P2 minus P1, you want to measure P2 minus P1 equal to, okay, the H2 minus H1 into rho g. So, this is the pressure with the rho into g. So, there is a pressure drop delta P. So, here another one is, you see the difference whatever the vessel, water shape of vessel, but the pressure is same. You just see here the P1 is same for here and the same P1 and here also P1, and then you take the pressure P0, the throughout the surface same, the P0 is same, it does not matter what type of vessel, but the wherever this, okay, this one the P0 at point, this point always, okay, same way here also the pressure P1 is also same. If I want to calculate the P1, then of course the P0 plus how much the H1 and into the rho g, okay, this is called as the total pressure. This one P1 we can calculate, the P1 here, the P1 equal to, so you take a P0 plus this H rho g, okay. So, now we discuss about the pressure, the head of the fluid. So, very simple, because we know what is H here. So, you can take directly, because already you know P equal to H rho g, you take H equal to P by rho g. So, the head of fluid we can easily calculate from here. Of course, now always we are talking about pressure, but how to measure the pressure? Of course, all of you know that the pressure measure we will use for manometer. How the manometer mainly they use for the chemical industries and other industry processing plants, definitely they will use for the pressure measurements, that one. So, here mainly the flow meter depend on the pressure or pressure difference we can measure here. The best example I already discussed is a manometer. The manometer is the device for the measuring the fluid pressure. So, it is conditioned like bent tube, U-tip, whatever, okay. The tube containing like bend, it is called a bent tube here. It has different specific gravity here. So, using manometer generally we can discuss about the pressure. So, some case we will discuss the pressure difference here, but I will just give one example, so that we will get a thorough idea how the manometer works. So, here simple U-tube manometer, and the PA is the pressure at 1 ohm, the PA is the pressure at 1 ohm, then at the other is the PB is the another point, okay. It is like U-tube. So, both pressure P and B we have this one, and again we have two liquids, one is the liquid B, that is called density of rho B, and then other one is for the density of rho A, but both liquids are immiscible. I can explain through this one. Yeah, this is a pressure 1 ohm PA, so other one is pressure PB. You just take a totally 5 points, the point number 1, then point 2, then point 3, point 4, point 5. Okay. So, here I already discussed this, we have two type for different type of fluids here. The first one is for fluid B, that is rho B, then other one is a rho A, the fluid A, then again here also the rho A. Okay. So, we know what is the value of here. So, you take a P2 to P3, P2 to P3, then this point is again a rho B, okay. But we want to measure the P2 to P3. So, P2 to P3 we have to measure. So, here you take first P2, but up to this the P2 point you take PA, then the height is Z, the height is Z, here height is a Z, then R, okay, then the density of fluid is rho B into G. So, the first point is P2 over, P2 done now, then you take a P3 at point 3, P3 the summation of PB, then because we have two different type of fluids are there, the one is for rho B, so PB plus Z into rho BG, the first point, the second one is for the difference, the height is R, but the density of fluid is here rho A, then G. So, then we have to add this also. So, we can write this side PB equal to the point P3 equal to PB plus the PB is here, then add this Z, then plus R, okay. That is only we added here. For this point everything same, that is only we are just giving Z plus R, but the density of fluid is rho B. So, we make it equal, then finally we get the pressure difference very beautifully, the PA minus PB equal to pressure drop delta P into R, into the R is the height, the head of that one, okay, head of that one, the density difference into G, because since we are using the two different density, and then this one is very simple for U-tube manometer, we explain that one, okay. So, another simple problem, you just read the problem. The large storage tank contains, the density is 917 kg per meter cube, but the tank is totally 3.6 meter tall, it is a open atmospheric pressure this one. So, the tank is filled with the oil up to 3 point this one, then also contains a water is a 2 feet, the first 10 feet is oil, then another is the water in the bottom tank, but calculate the pressure in terms of Pascal, they are saying in the 3.5 meter for the top of the tank or the bottom. So, I will go to the problem, maybe you get idea. So, here same thing, the pressure P0 here 1 atmospheric pressure, and other one is the oil P1, the height is 10 feet, the H1, then the water here, water is the height of that one is a 2 feet. So, the first is a 10 feet. So, here the first point, the pressure we have to measure P1, the P1 is this point, whatever I explained same thing P1. So, here P1 equal to, we have to take P0 plus H rho G. So, the P0 value already we know 1 atmospheric pressure, then height of course you know that one, how much height we are using here. The density of already the problem given, the density of first oil, the density of oil also already the provided here, the 917 kg per meter cube, density of oil, of course gravity this one, then we will get the value of P1. So, the P1 we can calculate very easily this one. Same way for P2, the pressure at the bottom, the B2 is the pressure at the bottom, the P2 is the summation of the P1 plus this one. Already we calculated P1 value from here, P1 value. So, then again this we have to use for another point. So, here P2 equal to P1 plus H rho G of water. The height of this one here again the 2 feet of water here, that you have to use here, the height here. Then rho density of water 1000 kg per meter cube, and the given the gravitational force. So, we will get the P2 at point how much pressure here. So, that is a very simple problem for to explain, okay, the biotechnology of rather this one. So, what is the pressure at point 1 and point 2 different this one, okay, because this the first one is for P1 in oil and then P2 at the water point. So, today the class, the key takeaway here, we just talk about the rheology studies, because already I discussed rheology is the flow of study, the flow of studies, how the deformation flow occurs in the very simple the biological system here. And then again definitely the flow property mainly depend on the mixing efficiency, then oxygen transfer, then heat transfer, movement transfer. Anyway, we will discuss one by one very thoroughly after some time. We will do some MATLAB programming also. Then understanding the shear and the flow is essential of equipment design. Then we also understood that one. Definitely when you want to go to lab scale to pilot scale, you need definitely the flow of the aspects, otherwise it is very difficult to do bioreactor here from lab scale to industry level. So, that is only we discuss here. This is a key takeaway point. Thank you.